Folks, today we're going to be investigating the relationships in volume between particular shapes. So, it says here, in the past, like meaning grade 7, grade 8, maybe even before then, or maybe even a little after then, we've been working with determining the volume of particular three-dimensional shapes. And in today's lesson, we're going to be having a really close look at prisms and their pyramids. Yeah? So I have this first example here. Notice we have some sort of rectangular based pyramid over here on the left. And over here we have some rectangular prism or rectangular based prism, whatever it is you want to call it. Now, we are able to calculate the volumes of these. We have the formulas on our EQAO formula sheet, right? Maybe we could even just write that here. EQAO formula sheet. I believe when I printed it off for you, I believe it was blue. Okay. Yeah, so we could look at the EQAO formula sheet and calculate the volumes of these things. Great. I don't actually want us to do that right away, but I do want you to know that you do have the formulas to do that on the EQAO formula sheet. Instead, the first thing I'd like you to think about here is, what do you notice about the height, okay, and the base, and the base of the prisms and pyramids we have? So let's first perhaps look at the height, okay? Both of the heights look like, well, in this pyramid here, the height is certainly 3 yards. YD is yards, so it's 3 yards. And in the prism over here, looks like the height is 3. So we can go ahead and put H here. And we might even write, okay, the height in the pyramid is 3 yards. The height in the prism is 3 yards. Yeah? That's what we noticed about the heights. The heights are equal. They are equal to one another, yes? They are both 3 yards. Yes? In the pyramid it's 3, and in the prism it's 3. The heights are equal. Next, let's talk about the base of these objects, the base. The base face, yes? The base face. So when we're looking at the pyramid over here, we're just looking at this base face. So basically we're just looking at the rectangle at the bottom, okay? The rectangle at the bottom has dimensions 4 yards by 2 yards. You see that there? Okay, so I guess, the base area, okay, we're talking about area, the base area would be 8 yards squared, because 4 times 2 is just 8 yards squared. Let's have a look at the prism, right? We see this prism here. It has the same dimensions. It is also 4 yards by 2 yards, which means its area is 8 yards YD, and then we got to put squared. So let's write this down. We could say the base area of the pyramid is 8 yards squared. The base area of the prism is 8 yards squared. So what we notice about these two shapes is that they have the same height of 3 yards, and they also have the same base area. Yes? The base area of the pyramid is 8. The base area of the prism is 8 yards squared. Okay. Now, when you're dealing with prisms and pyramids that have the same base area and also the same height, there is some magical relationship that you're going to see. And the best way to see it is to actually see it. There's no other way. So what I mean by that is, well, how many of these pyramids do you think will fit inside of the prism? Like, I'm not talking like imagine this. Imagine we can melt down the pyramid into some sort of liquid, and then we could just dump that into the prism. So imagine how many pyramids will fit inside of the prism? Maybe take a moment, think about it, talk about it. Maybe guess. In the past, some students said 5. Some students said 4. Some have said 1. But whatever it might be, take that guess with you, and we'll see what actually happens here. How many pyramids, does it take to fill a prism? Now that is, they do have the same base area and height, okay? So what I've done here is, we've got some video. So on your end, it doesn't really look this pretty, but on my end, we have a nice YouTuber. Think about how many square-based pyramids fit into a square-based prism. And keep in mind, okay, this is pretty important stuff to remember here, is that they have the same base area and height, very similar to the other ones. So let's go ahead and watch, shall we? Should I full screen it? Oh, I can't even if I wanted to. So that's 1. Okay, that's the volume of 1 pyramid in the prism. Here comes the second one. Oh, okay. 2. 2 looks almost full. Are we going to fit a third one, you think? All right, let's see here. Whoa. Whoa, okay. It looks like it's exactly 3. Exactly 3. Exactly 3 pyramids fit into the prism. Yes? They have the same base area and height. All right. Now, what about triangular-based pyramids and triangular prisms? I mean, maybe the triangular-based pyramid is not on your EQAO formula sheet, but they would be a combination of prism pyramid that would have the same base area, yes, same base area, and height. So let's see what happens here. We're filling up the triangular-based pyramid. All right, there's 1 into the triangular prism, believe it or not. Here comes a second one. Is that full? Look, all right, I don't know. Let's see what we got here. Is that full? Oh, I think there's like a line there to show the actual fullness. I see. Okay, exactly 3 as well. Look at that. Look at the surface tension on the water there. Oh yeah, get in there. That's awesome. Okay. And okay, 2 for 2. We got exactly 3 pyramids fitting into 1 prism. What about cones and cylinders? What about cones and cylinders? Because a cylinder is like it's sort of like a prism. I think it's like a circle prism, I guess. But then the cone would be like the circle pyramid, I suppose. So let's go ahead and see how many of these cones fit into the cylinder. Again, they would have the same base area and height. Yeah, I think it's kind of demonstrating the same base area there and the height. So we got 1 cone. Oh, that looks less for some reason. I don't know why. Okay, here comes the second one. Phenomenal. Okay. And the last one. Now, okay. Doesn't look like he's going all the way to the top, but I think there's like a piece that can go on the cone, and it like closes it at the bottom. So like if you didn't want any liquid in there. But again, you notice there's exactly 3. Exactly 3. Now, we could argue that okay, it was a little over full, or it was a little less full, or whatnot. But it is what it is. It is actually exactly 3. It's exactly 3 cones fit into 1 cylinder. That is that the cone and cylinder have the same base area and the same height. Okay, that's the stipulation. Okay, so let's conclude here. What is the relationship between the volumes of prisms and pyramids with the same base area and height? Well, if we go back to that original one that we had at the front, you might have to draw this on your own page. So you can draw this rectangular-based pyramid, and you can draw the rectangular-based prism. And what we're going to do is we're going to calculate the volume of each, okay? Because these undoubtedly, okay, they have the same base area, right? 4 by 2, which area of 8, yes, and the same height, right? Height of 3. So we're going to go ahead and calculate the volumes of each of these. So to calculate the volume of the square, or rather rectangular in this case, based pyramid, I think on your EQAO formula sheet, it'll say square-based pyramid, but square or rectangle, it'd just be length times width instead of b squared. We have length times width times height divided by 3. We plug in our length, width, and height, so 4, 2, and 3. We go to the calculator. We go 4 times 2 times 3 equals 24 divided by 3. And sure enough, we have 8 divided by 3? 8? Yeah, 8 yards cubed. Notice how we're talking about cubed today because it is volume, right? It is volume. And the rectangular based prism. That formula for volume would be length times width times height. And what we're going to do is we're going to sub in the values of length, width, and height, right? We'll sub in 4 for length, 2 for width, and 3 for height. And 4 times 2 times 3 is 24 yards cubed. Okay, so what do we notice here? Well, we said that there's 3 pyramids can fit into there. Yes? So the volume of the pyramid times 3 would equal the volume of the prism. And is that true? Is that true? Let's have a look. 8 yards cubed. If we take 8 yards cubed and times it by 3, it equals 24. So look at that. The math speaks itself. Yeah? Likewise, if you wanted to go the other way, you could also say this in the opposite way. You can say, okay, well, one prism is, now you could say divided by 3 here. You could, but let's stick with multiplication. We'll say times by 1/3. Because timesing by 1/3 and dividing by 3 is literally the exact same. So we could say that, well, the volume of the pyramid is 1/3 the prism. Or the volume of the prism is 3 times the pyramid. Yeah? You might have noticed something in these formulas here. Let's have a look at these formulas, shall we? Let's first look at this formula for the pyramid. Length times width times height divided by 3. And the formula for the prism is just length times width times height. Interesting. You might be able to see where the volume of the pyramid came from, because all they've done is they've taken this volume here, and it looks like they've just divided it by 3. And that's exactly the relationship that's going on between these two. In fact, perhaps that could be true for cones and cylinders. Let's have a look. The volume of this is right from your EQAO formula sheet. I copied and pasted it. So we look at the cylinder, okay? Its volume equals pi r squared times height. Great. Then you look at the volume of a cone, and its volume equals pi r squared times height divided by 3. Interesting. Or you could say 1/3 of pi r squared times height, which is the same thing as dividing by 3, just like we talked about before. So, really simply put, that is the relationship between pyramids and prisms that have the same base area and height. Now, let's oh, of course, we have the same thing going on here. We have length times width times height. Now, in this case, if this is a rectangular-based pyramid, if it were a square-based prism, if it was a square-based prism, it would just be V equals B squared times height, where you'd have some sort of, let me try to draw this with the pen, some sort of square, and then another square up here, yes, and it would look something like, oh, whoops, okay, let me try this again. Draw a square, and we kind of can connect, yeah, I mean, it's kind of hiding behind there. Not the best diagram, but nonetheless, we see over here we have b squared times height divided by 3, or just 1/3 of b squared times height. Yeah. So maybe let's try some. Should we just try some for funsies here? So you don't need to write this down, or maybe you could. But let's just pretend for all shapes. We'll say this. We'll say all 3D shapes, or all pairs of 3D shapes, have the same height and base area. Yeah. That's our disclaimer here. So let's go ahead and think of, I don't know, some sort of cone. Yes, this is a cone. Believe it or not, there it is. Not bad. That's a cone. And over here, we have a cylinder. Okay? That's actually pretty good. So let's just, for argumentative sake here, say that the volume of this cone is 30 meters cubed. Yeah. If that's the case, then what is the volume of a cylinder with the same base area, right? Same base area. They got it. They got the same base areas and the same height. The same height. Well, you might be thinking to yourself, okay, there's going to be some sort of relationship here. We know that 3 cones can fit inside 1 cylinder, so the volume here might just be the volume of the cone times 3. So we could say that would be 90 meters cubed. Yeah? Likewise, we can try to go the other way around here. We can draw some sort of square-based pyramid. I'm going to try my best here. Squares are not my forte with drawing with a mouse, but let's try it like that, shall we? Yeah, that's a little bit better. There's the top, and then what we're going to do is we're just going to connect. Boom. Boom. Not great, but not bad. Let me just quickly try that again here, folks. That is not great at all. Yeah. Kaboom. And then we'll connect. I mean, it's not that great, but I think we get the idea here. We have that pyramid, or lack of pyramid, and then we're gonna have some sort of prism here, shall we? Yes. Here we go. And believe it or not, these two shapes have the same base area and height. Okay? They do, I promise. Let's just say the volume of this is going to be, I don't know, let's go with 120 centimeters cubed. Yes? The volume of this square-based prism is 120 centimeters cubed. If that's the case, then what is the volume of a pyramid with the same base area and height? Well, again, you might be thinking of some sort of relationship here. You could, think of 120 centimeters cubed. You could just divide it by 3, because you know that 3 of these can fit inside 1 of those. Or you could take the 120 and just times it by 1/3. It's the same thing. You could divide it by 3 or times it by 1/3. We go to our calculator, and the calculator says, oh, hey, this has got to be 40 centimeters cubed. Okay. Now, I think you get the idea, folks. There is homework here. I believe it looks like I assigned an outrageous amount. I think it was like 1 to 11 and one more on top. And I know it sounds like that's going to be a lot. But truthfully, these questions don't go A, B, C, D, A, B, C, D, E, F, G. They're just kind of like one and done type of questions. And what I ask is that as you're going through these questions, they will go quick, I promise. They certainly will. And when they do, I ask that you do check your answers as you go. So when you finish the first one, go and check your answer, check mark it, and then move on to the next. Yeah, and so on and so forth. folks, hope you enjoyed this video lessons with my decent or maybe not so decent looking diagrams. If you do need anything, please feel free to visit me in the Math Help Room, or send me an email, or chat with me in class the next day. All right, folks, take care.